Okay then. Today I'm going to start a chapter 2. So what we had up to this point was chapter 1, and we started just looking at the very basics and concepts that we are going to use in the rest of the book. So whatever we learned so far was just concepts and three important laws, the two Kirchhoff laws and the Ohm laws. Uh, from this point, we actually start to analyzing a circuit. We are start to learn how to analyze a circuit. And how it goes is that first we start to analyze the DC circuit that only has the resistance into that. And we'll look deep into that, how to do that. And after that, we'll start to add other elements into the circuit, like capacitor, and see if we have other elements in the DC circuit, what would happen in addition to resistor. And then toward the end of the class, we will start to look at the whole things that we look at, but for the AC, for the alternative current. But the very first step, and it's probably the most important step, is that we start to look at the circuit that has a DC current in that. So everything is DC, is the direct current. Nothing changed over the time, in other words. And only has the resistance, doesn't have any other element into that. And we learn how to analyze that. There are different methods of analyzing, so we learn all of them. And by the time we learn them, by the time we go to the next chapter, which we start including other elements into the circuit, or we start to look at the AC, basically what we are going to do is that we use whatever method we learn in this chapter for the pure resistive circuit, and then use that method for other elements or for the AC current. So it's very important to to really learn this chapter, because it's basically what we are going to, whatever analyzing method we learn in this chapter is what we are going to use for the rest of the book, throughout the book that we do. But for now, what we are going to do is a chapter 2. We start a chapter 2, and we only start to look at the DC circuit that only has resistance. It doesn't have anything else in that. So before I start to talk about the different method we are going to use, the very first thing, we touched it in the last chapter, but we look it in deeper in this chapter. We are looking at the last chapter. We are talking if how's the condition if we say that elements are in series or elements are parallel. And now how we are looking at that in the perspective of just resistance. How it's going to be if we have the resistance in series, or what's going to be if we have the resistance in parallel. So I start with the series resistance, easier. So if you remember when I was talking about having the elements are in series, it was like that. One element comes right after another element. So the end of one element directly connected to the end of another element without any other element be in between, and there would be in series. It's the same thing for the resistance. So if I have the resistance like that, and then it follows by another resistance, and then it directly followed by another resistance. If you have something like that and it just keep going, these are in series. It means that one of them connected, one end of that connected directly to the end of the other element, and there's nothing else in between except one wire. So if I have the resistance like that, and then it goes there, and then the resistance like that, and there's a wire here, this is not series, because although the end of them are connected together, but there is the third element in between them. There's the third wire in between them. So this is not, it should be only a single wire, nothing else between them. Then you will say that these are in series. If there's anything between them, even a single wire, then they are not in series. If I have this, for example, and this one has the resistance of R1, R2, and R3. So, and it can be as many of these one. I can say this one is equal. I can replace this with a single resistance like that and call it the equivalent resistance. So I can take these three out and only replace them with one resistance. And that resistance, when we're talking about that, is just going to be that the Req is just add them together, just R1 plus R2 plus R3, and plus if you have other more resistance in series, you just add them together, and that's what you're gonna have the equivalent one. So I can take these three out and just replace them with one resistance, and that I use that resistance in my calculation. So one important thing is that, for example, if I have a circuit like that, assume it goes like this, like that, and then it's connected to some kind of, assume it's a positive, negative, and some kind of current goes through that. So if I have the current go through that is I here, so this is the R1, R2, R3. The current goes through all these three is I. So it's I go through R1, I go through R2, I go through R3. They have the different voltages. For example, for example, this one is the V1, this one is the V2, this one is the V3. So they have different voltages, but they all have the same I. So because whatever I goes through this one comes out of that, then goes to the next one, comes out of that, then goes to the next one. So I is going to be the same for all three of them. When I replace them with the equivalent resistor, so like that, it goes there, and assume I replace them with single equivalent resistor like this, and then you have that positive, negative, and then when we have it here, if the voltage in this one is not V1, is not V2, is not V3, is another V. So if this is it's going to be the equivalent resistance. Then it has the V, it has the voltage in it, which is not equal to V1, it's not equal to V2, is not equal to V3. But whatever current goes through that is I, is exactly the same as I go through the R1, I go through R2, I go through R3. So if I calculate the I in the equivalent system here, whatever I find here is the same as the I have here. So that's when we have in the series, the I is going to be the same in the equivalent one and in each of the original resistor we have, but the voltage is not going to be the same. So you have V1, V2, V3, and you have another V here. So they're not going to be the same, but the I is going to be the same in both original format and the equivalent format, and that's what we are using it. It's very important when we are analyzing it, we use it to find the I. Remember, again, at this point on, when we are talking about analyzing a circuit, basically what we are talking about is just to find the I and V in every element in circuit we have. So when I said, okay, we want to analyze this circuit, means go ahead, find the I and V in every element. In most cases, that's all we are going to do. Nothing else we are going to do that. So this is if you have the resistance sitting in series, so very easy, just add them all together. That's all you need to do. Replace them. So when we are analyzing the system, if you have resistance sitting in series, to simplify our circuit, we just replace them with the single equivalent resistance, then solve it, and then we bring the I back to each of those original elements, and then resolve the circuit for those original elements. So the next one was that, again, we remember the last in the last chapter we talked about the parallel element, and when talking about the parallel element, it was like that if we have the elements that all the first end or all the one end are connected together and all the second end of all of them connected together, there would be parallel. This is the same thing as we call it for we talk about the resistance. So if you have the parallel so what would happen if you have the I would draw it like that first, it's easier to understand. So if I have three resistor like that, and so if I have this resistor R1, R2, and R3, if these three are connected, I should say the first end of them, the first end of all three connected together, the second end of all these three also connected together, so they are in parallel and in parallel format. And if they are in parallel format, what we can say that we can replace this with again a single resistance. So I take out these three, or it depends on, doesn't matter how many you have, you take out those and replace them with one single equivalent resistance. And that CC resistance, if they're in parallel, it's going to be 1 over 1 over R1 plus 1 over R2 plus 1 over R3 R3 plus if we have more. So this is how we are gonna find the equivalent resistor if they are in parallel format. Again, one of now, for example, see when we are talking about the series, when it says that the I is the same and the V is different. Now let's look at it, for example, a simple circuit that we have. If you have the circuit like that, and there are three resistors in that, positive, negative, and then we have the R1, R2, and R3. So we have these three are in parallel, and as you see, because these three end connected to one node, and these three end also connected to the same node. So these three are in parallel. It's just the same things here. I rotate it. So these three connected to same node. These three also connected to same node. So these are in parallel. And remember, when we were talking about in parallel, if you have the I going in, then that I would be goes here as I1. Then you have I2, and then you have here I3. So that I is just the Kirchhoff law. It's gonna split into three I's. So I1, I2, and I3. So you have different three I's. But if there's a voltage here, V, this is also V, this is going to be V, this is going to be V as well. So in parallel, they all have the same voltage but different current. In the series, they all have the same current but different voltage. In the parallel, they all have the same voltage but different currents. So if I go ahead and said I want to replace this with the equivalent one, so I take them and just replace with equivalent resistor, and says that okay, this is going to be Req, then I know that what's going in there is I, and then what is the voltage has is V. So when I have the I, if I come here and calculate the I can't say anything about the I1, I2, or I3. So the I that goes to the Req is not the same as I going to either of these R1, R2, or R3. But if I find the V here, the V is going to be exactly the same as V in R1 or R2 or R3. So if I simplified my circuit to this and then find the V, then I can bring that V back to either of these R1, R2, or R3 and solve that circuit. So that's a very important point. If we have in the equivalent resistor, we cannot bring the I back to I1, I2, or I3, but we can bring V back, because whatever V is here is the same as V here. So you can just put the V back here from the simplified circuit and then start to analyzing the more complicated circuit when we want to do that. One case of that you don't need to memorize it, but it's good to know it, sometimes very handy, is that if you have only two let me draw the one. So only if you have two parallel resistance like that. So if you have only, so R1, and then you have R2, the equivalent R is just the same as this equation, is 1 over 1 over R1 plus 1 over R2. And if you simplify that equation, sorry, it's EQ. If you simplify that equation, what you get is R1, R2 divided by R1 plus R2. So I don't want to say that memorize that, but remember that if you have only two, this equation would be eventually, if you rearrange it, you will get to this equation at the end. Sometimes it's easier just remember that for most cases that have two R, so easier to do it that way. But either way, you should be able to easily just punch it in your calculator this way or this way and get the value for the R. So let's look at a very simple example, see how actually we can use them. So it would be like, assume I have a circuit like that, so it's going to be R1 and then there is a R2, the R2 and the 20, and then there's a R3 is 5, 5O, and it's 4. So the R4, and this is 15O. So assume this is the circuit we are given, and we want to simplify that circuit. So it's a part of the circuit we are given, and we want to simplify that circuit. So when we are given the circuit, we have to go ahead and look at that and see how we can simplify it in a way that we can use it. If I look at this circuit, so if I look at that, so with respect to any of the other, it's not either parallel or in series. So I can't do anything with this one. The same here, if I only look at this one, again, it's not in parallel or series with any of the other, it's not in parallel with any of them because this end is here, but the other end doesn't connect to that, and it's not in series because it's not going end to end with any of the others. So the only one that goes that fit one of the parallel or series format are these two, because this one goes right to the another one without anything between them. So this one and this one goes right into this one, nothing between them. So these two are in series. These two are neither in series or parallel. So these two are in series. So I would say that this one is equal to, so this one is going to stay there, that R1. And then here also this one is, I don't want to do anything, so the R2 is going to stay there as well. But these two are in series, these and these are in series, so I can add them together. And then what I'm going to have here, if I add them together, is that I can say REQ for 3 and 4. The equivalent of the 3 and 4, they are in series, you just need to add them together. So it's going to be 5 plus 15 is 20. Oh, so these two are in series. Again, R1 and R2 is just nothing, so we leave them alone. These two are in series, so because they are in series, we add them together. So 5 plus 15, and then we have 20 ohm. Now that we have it in this case, I will say that now I can say this REQ for the 3 and 4 and R2, these two are in parallel. Now I know that these two, again, still these ones, the R1 is neither parallel or series in with either of the R2 or REQ, but these two are in parallel. So I can go ahead and say that again, it's going to be equal. So R1, I just leave it because it's not parallel or series or nothing. I leave it there. And these two are parallel, so I replace them with the one resistor here. And then this one, again, is going to be the equivalent of 3, 4, and 2. 3, 4, and 2. 3, 4, and 2, these two. These are in parallel, therefore, because they are in parallel, they are going to be 1 over, and here is 1 over 20. Plus 1 over the resistance of the R2, which also is 20, if I'm right. And if we do this calculation, and if I write everything right, it should come out at 10 ohm. And now look at these two. Now these two are in series because one of them goes right to the other one. There's nothing between them. They're directly connected to each other. Now these two are in series. So I can go ahead and say, okay, so these two are in series. So I replace them with one final equivalent resistance like that. And then this is going to be my or you can write it 3, 4, 2, and 1, but or just like that. And then you add these two together, because in series we just add them together. The R1 is 10, and this one is also 10. So it's going to be 20 ohms. So this is the eventual, when we simplify this circuit, this is what we are going to get. And then we start to analyze the circuit from this point, and then we go back to this, and then we go back to this, and then we go back to this one. And in the example, we'll see how we will do that. So now I'm going to start to talk about the very first method of how we analyze the circuit. And that very first method is that to use the concept of being parallel and series for purpose of analyzing a system, or in other words, for purpose of finding the voltage or current in the circuit. So, so the network or circuit analysis by this is probably the easiest way that we can start analyzing a circuit. So unfortunately, there are lots of circuits that cannot be fit into these methods. It has very own limitation, and its limitation is that you should have the parallel or series resistance in the circuit. But if you come in the way, if you look at your circuit and you see that all the elements are in series or parallel, that is the way you should choose compared to other more complicated methods that we will learn later on. So anytime that you're given a circuit and they told you to analyze it, and they are not specific what method to use, if they tell you whatever method you want to use, the very first thing to do that, just look to see if you can find any parallel or series elements in the system and replace them with the equivalent one. By simplifying your circuit in this way, in most cases you can solve it very easily. Again, I said not all the circuit has the parallel or series element, and it's not that there are lots of circuits that you cannot use this method for them, because you are not going to find any parallel or series element. But if you do, probably your best bet is to go ahead and replace the parallel or series element with the equivalent elements, simplify your circuit, and then start to analyze. How this method works is that, again, I said, most of the time, first look at all over your circuit, but most of the time you will find, or you need to start from the very far end from the source. So wherever your source is, your parallel and series elements are most likely the farthest away from the source. So you have to go and look at whatever you have the farthest away from. So it's not always the case, but most of the times the case. So whenever you have it, where is your battery, just go all the way away from your battery, and then start looking at the elements, see if you can find any parallel series. After you find them, the next step is that replace them step by step. Don't replace them all together at once. Step by step, replace them, like what we did with the previous example. Step by step, replace them with the equivalent, and keep simplify circuit until you cannot simplify it anymore. Then from the very last step, from the simplest circuit you have, analyze everything, and then bring back all the current and voltage to the previous step. Analyze that, bring all the current and voltage to previous step and until you get to the original circuit. So one more time, when you have the circuit, one step at a time, start to simplify it by using the equivalent series or parallel. So one step at a time. So one step at a time, simplify it, then simplify it once more, then simplify one step more, then simplify one step more, until you get to the simplest format you can get. Then analyze the very simplest circuit. Then whatever value you get, bring it to the previous step, analyze that circuit, bring back to the previous step, analyze that, and do it until you get to the original circuit. I'm going to show you how to do that with an example, and you will see how we can use this method. So assume we are given the circuit like that. So we have a battery. The 90-volt battery is the 90 volts battery as a DC, as I said. We are working in this case, and then it's connected to 3 resistance. So we have the R1 here, 10 ohm, and then we have the R2 here, which is going to be 30 ohm. So the R2 is a 30 ohm, and then we have the R3, which is 60 ohm. So we are given this, and they are asking us to analyze this circuit. If simply they ask us to analyze it, it means that find the current and voltage for each element in the system. Forget except for the battery. So everything else you have, find the current and voltage for them. If they just simply say analyze it, means find the current and voltage in R1, current and voltage in R2, current and voltage in R3. So when we have something like that, this is how we are going to do it. Again, one step at a time, we are going to start to simplify that. We look at this and see, and I said, most of the time is the farthest away from the sources. So again, this one is not either in parallel or series with any other element. So I ignore it for now. So if you look at these two, R2 and R3 are parallel. So both end of them. So the first end connect to one node, the second end also connects to one node. So these two are parallel. So I will go ahead and replace these two with a single equivalent resistance. And again, I will say that make sure you do it one step at a time, because if you have, for example, also other parallel or series, don't do all of them at one steps until you're really comfortable with that. If you have, for example, other 2 parallel resistor, just leave them alone, do one step at a time, and then in the next step go to the next parallel or next series, just one step at a time. So I would say that, so this is going to be equal to this. So it's a 90 volt here, plus minus, and then I have the R1 here, and then I replace these two with the equivalent resistor. And if you look at them, these two, I will write here, for example, this one is going to be R, the equivalent between 2 and 3. If you look at this, so I can say that because these two are in parallel, I can say that R eq for 2, 3 is 1 over R2 plus 1 over R3, which is going to gives me 1 over 30 plus 1 over 60, which if I've done everything right, it should come out at 20 ohm. So I can say that, so this one is going to be 20. Oh. Now these two are in series. So I can look at that as R1 and RQ are in series. So what I can do is that I can go ahead and say, okay, I replace these two with a single one. So I would say that it's a 90 volt again. And then there's the equivalent resistance for both of them. And this time I have this RQ, and it's just is add the R1 and RQ2. So I can go ahead and say, for example, the REQ. You just add these two together. So R1 plus REQ 2 and 3. So add them together. So R1 is 10. And REQ here 2, 3 is 20. So it should come out at 30 ohm. So we're gonna go ahead and say, okay, this is 30 ohm. Now I have, this is the most simplified version that I can have it for my circuit. Now I start to analyze it from here, and then I go back to this one, and then I go back to this one. Here, if you look at it, it's very simple because the resistance connected to the 90 volt battery. So the voltage in the resistance is 90 volts because there's nothing else here. And the Kirchhoff law, so you remember the quiz we had, the last session we had, it was a simple like that, we analyze it. This one is directly connected to this one, and so the whatever voltage it has the same voltage. So the voltage here is going to be also 90 because there's no other elements is in the system. There's only one resistor, one battery. So whatever voltage the battery has, this one is going to have the same voltage as well. And then I can here write it here that V is I REQ, and if this is the I, and so if I write this, it's going to be the V is 90 volts. So 90 volt is the Ohm law that we had it is equal to I, and the REQ is 30. Therefore, the I would comes out at 3 amp. So I can say the I is 3 amp here, and the voltage is 90. Now I have the I and V, and I want to bring them back in here. Now I have to be careful which one I can bring back, which one I cannot bring back when I will go back here. The I can bring it back here because the I is exactly the same. Whatever I goes through this element, it goes through these as well. So this I can bring it back and says that, okay, the I is 3 amp. But the voltage, this 90 voltage, I cannot bring it back because here, if you look at now, I have two elements that based on the Kirchhoff law, and I have one loop. If I add all these voltage together, it should become 0. So R1 plus the voltage in this one plus the voltage in this one should be equal to voltage from the battery. So I cannot bring the voltage back, but I can bring the I back because, as I said, this is a series. Remember when I was talking about series, whatever I goes through this one is the same as I go through these, either of these two. So I can bring the I back, but not the V. Now, if I bring the I back, look at here. So for these cases, what I can write here. Here, I know the R1 is 10. I know the R1 is 10. I know the R, I know the I. So I can use the Ohm law for this one here. So I can go back and say that for the R1, so in R1, I can say, write the Ohm law. So V1, whatever is that, the voltage here, is I1 is I basically, because I1 is I, and is the R1. So the V1 is I, which is the 3 amp, times the R1, which is the 10. It's going to give me 30 volts. So I know that, okay, so it's going to be 30. Then these two, the voltage here, assume I call it the V for 2 and 3. The same I also can write it for here. It's the same also I can write in R EQ 2, 3. I can write the V 2, 3 is I, again, is the Ohm law, EQ 2, 3. So the voltage in 2, 3 is I, which is the 3 amp, times the equivalent resistance here, which is the 20, which is going to come out as 60 volt. So this one is going to be 60 volts. Now I have the I in both this element and voltage in both this element. So I have the I and voltage in both elements. Now I bring them one step back here. Now I want to go back. So if I want to go one step back, so the I here is the same. So this is the I, 3 amp. But this I will be divided into I2 and I3. Well, basically here is the I3. Is also is I3 here. So the I comes here at this node, it breaks into 2. So I cannot bring any, I only can bring the I here. For each voltage, the R1 voltage is the R1 voltage because it's the R1. We didn't combine with any else. So I would say that the R1, so the voltage for this is 30. Now here, look at that, these two are in parallel. And this one is equivalent of the parallel. Remember, when we have them in parallel, I said that the voltage in the equivalent is the same as the voltage in each of the original one. One more time, when they are in series, like here, the current in the equivalent is equal to current in any of the original one. When they are in parallel, the voltage is the same as the voltage in any of the parallel ones. So let's go back and show you one more time. So if it's in series, the current in the equivalent is the same as current in the original resistance. If it is in parallel, the voltage in the equivalent one is the same as the voltage in the equivalent one. So again, here, what we have is that, so these two are parallel and this is their equivalent one. So the voltage in these two is the same as the voltage in the equivalent one. So here, the voltage in V2 is 60. And the same here, the V3 is also 60 because these two are parallel. Their voltage is the same as the equivalent one. And then if I come here and write for this one, so I will write it, I will write it down here. So for R2, so in R2, again, I can write the Ohm law. So I can say the V2 is equal to I2 R2. And therefore, I know the V2 is 60. And I don't know the I2. And I know the R2 is 30 ohm. So I2 will comes out as 2 amp. And the same in R3. I can write the Ohm law again. The V3 is I3 R3, and the voltage is 60, and the I3 we don't know, and the resistance is 60, and then we have the I3. This comes out as 1 amp. And as a check, you can come here and say at this node here, as a check, as this node here, the Kirchhoff current law, whatever ampere goes in, whatever current goes in, should leaves out. So 3 amp goes in this node, and 2 plus 1 amp leaves, which is because I3, how much is the I3? I3 is 1, and I2 is 2. So you see 3 amp goes in, and also 3 amps leaves that node out for that. So if you look at that, that's how we use the parallel or series equivalent to solve to analyze the circuit. As I said, this is this is the easiest way of analyzing the system. We start to simplify it one step at a time. And then from the very last step, we analyze it, we go one step back, we analyze it, we go one step back, and we keep bringing back the values, the values that we can bring back one step at a time until we analyze the entire circuit. The next two the next two parts that I'm going to talk about them is just the specific format of the parallel and series when we're talking them. So in very if the situation is in very specific format, then we can do the things in more simplified way. But this is the very special case of the parallel and series. What I talk about it. So what I talked up to this point was in general condition. If you have the circuit in general condition that you have some parallel or series element, how we can deal with them. Here there are two other special condition for these cases. And so the first one is called the voltage divider circuit. So the voltage divider circuit. If we have, and I explained it before, but I'm going to explain it again. If have the battery with a V is connected to, I'll say, so we have the battery that has the voltage of, and we call it V total, and then it connected to series of resistance. So for example, here, assume we have 3 resistance in series. It means that one comes after another, directly connected to each other, and then the last one goes back to the battery. So here you have the R1, here I have the R2, and here I have the R3. When we have these, I know that from Pearson that the I is going to be the same in all of them because in series. So I is going to be in R1 is going to be I, in R2 is going to be also I, in R3 is going to be I, because whatever goes to R1 leaves it and goes exactly to R2, leaves it and go to R3 and leaves it. So whatever current leave the battery goes all the way and then re-enter the battery, that current. So you know the I is the same. But also we know that the voltage is not. So we know that because in series, this is the V1, this is the V2, and this is the V3. And if you remember from the Kirchhoff law, it means that there's one loop. If I go ahead in one loop, assume if I rotate in that loop, if I add all the voltage together, there should comes at zero. All of them should become zero. And in other words, in this case, the V total, if you write the Kirchhoff voltage law and write it and then do the Kirchhoff voltage law, which says that sigma V is zero, you will get something like that, eventually you will get something like that. The V total, whatever the voltage that the battery provided is equal to all the voltage in the element. So you will get something like that, V1 plus V2 plus V3. Eventually you will get something like that. You will write that equation. Also for the R, we will have we can replace these three with R1 plus R2 plus R3. If you do some calculation and some rearrangement between these equations, eventually this is what you're gonna get this equation. So say that the V1, you can directly say that the V1 is the proportional to, it's gonna be R1, R, so it's the Ohm law. And if you use this here, this is what you're gonna get. It's gonna be V1 is gonna be proportional to R1 over R1 plus R2 plus R3. And if you have more, you can just add them. That V total. The same for V2. Can say the V2 is R, or write it the same as the other one. So it's the R2I, and it's going to be this R2 plus R3V total. And the same for the V3, which is going to be R3I. Sorry, R2, R3, R1 plus R2 plus R3 V total. In other words, the V total, it says that, look at here, I said the V total, if you add the V1, V2, and V3, it's going to be equal to V total. But V1, V2, and V3 are, the V total are splitted between the R1, R2, and R3 with this ratio, with the proportional to their resistance to the total resistance. So when you have something like that, you don't, and you have the V, you don't need to calculate any equation to find the V1, V2, or V3. You can go directly say that V1 is the proportional of this factor of the V total. So R1 over R total. Then the R2 over R total is the V2, and R3 over R total is the V3. So directly you can find the V1, V2, V3 without knowing the I. So the whole point here is that you don't need to know the I to find the V1, V2, or V3 in the circuit like that. So if you have the circuit like that, and you're asked to find V1, V2, or V3, one way is what we did before. Write the equivalent equation, find the I, and then write the equivalent resistance. Then in the equivalent circuit, find the I, and then comes back and try to find V1, V2, or V3. The other method, just right here, use these three equations and directly find V1, V2, or V3 without need of finding the I. This one is this condition is true for as many R as you have. So if you have 4, this one's going to be divided between 4. If you have 5, it's also the same equation. So you just keep adding it here. So if you have 4, you have R4 here as well. If you have 5 of them, you have R4 plus R5. So this format is true for as many as R you have in series condition. And in this case, so the total point, again, one more time, is that you can find the voltage without need to find the I. You can directly find the voltage in each of the resistors that are in series without calculating the I. So the next one, here is the voltage. So look at, I would say that before the voltage is divided between the R1, R2, and R3. So the voltage divided between them, and so the voltage divider. Then the next one is a current divider circuit. So in the previous one, remember that when I said that we have here the voltage connected to three resistance, and the voltage is going to be divided between R1, R2, and R3, and eventually if you add all the voltage in the R1, R2, and R3, is going to be equal to total voltage. So we are going to have the very same thing if we have the parallel resistance. So if I have a battery here, and this time, let's say source, so to make it easier. So you have a source, and that source has the I total. So it gives me the very specific amount of current, and this goes to two parallel resistance. It goes to R1 and R2, two parallel resistance. We know that in this case, the voltage in all of them is going to be the same. So whatever voltage this one has is going to be has the same voltage as here. So if it has the V, also the voltage here is going to be V as well. It's going to be V as well. So the voltage, because they're parallel, they have the same voltage, but the current is going to be divided. So if this I total is coming here, so if this I total is coming here, then it's going to be divided into I1 and I2. And we know that if I use the Kirchhoff current for this node and write the Kirchhoff current law, I know that the sigma I is 0 at any given node. So the I total is inter, and it should be equal to whatever leaves. So it's going to be equal to I1 plus I2. So it's what we know. Now, again, we can go ahead and replace these two with the equivalent resistance, and then try to find the I total, and then go back, find the voltage, and find the I1 or I2. Or in this very specific format, we can directly calculate the I1 and I2. So here the I1 is, again, it's a V over R1. So it's a Ohm law, but you can directly calculate it from this equation. So it's going to be R2 R1 plus R2. Remember, if this is 1 here, he's going to be 2 here. So if you have calculating 1, then it's going to be 2 here times I total. And then the I2 is going to be V over R2. And it's going to be R1. This time it's 2, it's going to be 1. R1 plus R2 times I total. So again, this is the same thing. You don't need to know the V to calculate the I1 or I2. So without knowing the V, you can directly use this part of the equation just by ratio of the resistance to find the I1 and so to find out how the I is going to be split between the R1 and R2. And this one, actually, these two equations, later on we use them a lot. Whenever we have the parallel resistance, instead of going and find the equivalent one, we just simply use this to find what's the how the incoming I, the total I, is going to be split between R1 and R2. We later on use the particular this one. We use the previous one, but we use particular this one to split the I1 and I2 without need to calculate the V. One important point about this one is that unlike the previous one, that we could have R1, R2, R3, R4, as many as R in series, this one is valid only for two resistance. If you have three, this one is not valid anymore. This one is only valid if you have two resistance in parallel, not more than two resistance parallel. So later on, as I said, particular this one, and also the previous one, we use it, in this case, we used to find how the I split, and in the previous one, we used to find how the V is split between the different element directly. We don't need to know, for example, here we don't need to know the V value. Now let's look at the example. The book had a couple of more examples. You can go ahead and look at them later on, but I just do one of them. No. So assume we have the battery. There's a 100 volt. There's 100 volt batteries, and then it's connected to R1 is 60, and then we have R2 is 30, and you have R3 is 60. So I think this is what we have. And we want to find what do we want to find? So now assume this is what we want to analyze. So here we want to start analyzing it. Again, to the first step, there's not much I can do with this one until I'm gonna simplify it into more simple format. If you look at it, these two are in parallel. So I would say that this is equivalent to having there's a 100 volt here, plus minus, and then I have the R1, which is going to be 60, and then replace these two with the equivalent resistor between 2 and 3, which we know that. So if I can do that, and I know that here, if I do that, REQ 2 and 3 are in parallel, so it's going to be 1 over R2 plus 1 over R3. It's going to be 1 over 1 over, so it's a 30 and then it's a 60. 30 plus 1 over 60, which if I do it right, it should come out as 20 ohm. So this one would be 20 ohm. So I know, now I know this one, it's 20 ohm. Now look at this condition. What if I look at this, one of the, I can go ahead and do from the original steps and start analyzing the whole thing, or I can look at it and say, okay, there are two two resistance are in series. So because there are two resistance, I can use the voltage divider to find the V here, for example, the Vx. So if I well, I said, for example, it's so here, if I call it the V23, the V in this one, I can directly say that I have the, in this case, I'll write it down here, the voltage divider. And the voltage divider, the V23, I can find the voltage, we don't know the current. And the voltage is the ratio of the, these two. So if I go back here, you see, the voltage is just the ratio of the resistance times the total voltage. So without knowing the I can go ahead and calculate that. So I can go ahead and say the voltage in this tree is directly the REQ23, ratio of that the R1 plus REQ23 times Vs, which is going to be V23 is going to be 20, and then divided by 60 plus 20 times the total voltage, which is 100 volt, and then it will comes out as 25 volts. So I don't know here, if you look at it, I don't need to calculate the I. I can directly go and find this voltage here for my calculation. And then now look at here, these two are parallel, these two are parallel. This is equivalent to the parallel because they are parallel. The voltage in the original one is the same as the voltage in the equivalent one. So I can go ahead and say the voltage here, also V2 is equal to V23 and is 25. And V3 also the same, V3 is the same as V23 and it is 25. So these two voltage has the same voltage as whatever I have in this case here. So we can bring them back for that case. Now look at here. If I go ahead and want to say that I'm going to find the I in either of these two, I can come here and calculate the I here in this case. So if you look at here, again, in this condition, if I have the I going in there, I can write the Ohm law in either, because I is going through this and I going through that. So if I write it for REQ23, I can write it that I, because whatever I goes through the V23 is equal to the I REQ23. Therefore, I know the V23 is 25 volts is equal to I, and this one is 20 ohm. Therefore, the I should comes out as 2.5 amp. And now I can also bring that I back here. And I know, so this is exactly the I here as 1.25 amp. Now I want to know how much I go through this one, through R2 and through R3. Again, the I split between two, so it's very the same as what we had before here. The I split between two. So although right now I have the V, but even without that, even without that, I can calculate the I. So I go ahead here and calculate the I without knowing that. So I can say the use the current divider and say that, for example, the I in 2 is equal to R3 divided by R2 plus R3 times I, which is going to be then the I2 is going to be, so the R3 is 60, and then it's going to be 30 plus 60 times the total I, which is 125. So it's going to be I2, and then the same we can do it for the I3 as well. So you can say I3 is going to be R2 plus R3 times I, which is going to comes out as R2, which is 30, and divided 30 plus 60 times 125. And then you can find the I2 and I3 directly without using the voltage. Also, because we already have the voltage, we also could have used the Ohm law to find the I2 and I3. So this is the usage of them. You can see them. It's very, it is the same concept, but a little bit just using a different way, but it's the very same concept of doing the voltage divider, current divider. Sometimes, as I said, sometimes it's going to be easier to use the voltage and current divider. Sometimes it's just easier to directly use the simple parallel and series concept to find the voltage and current. As we go throughout the rest of the course, you will find out there are some places, and we use them there. It's easier to use the current and voltage divider. So know the concept. Otherwise, you always don't get yourself confused. If you get confused with these two, you always can use the simple parallel and series concept to do the calculation. You don't need to get yourself confused with either of these two if you find them confusing. But in some cases, it just save you a couple of steps if you get comfortable with them in your solution.